In this lesson, we will look at the trends in the hydrocarbon properties as the number of carbon increases. The property that we're most concerned about is the melting point and the boiling point. First, let's look at a hydrocarbon in general. In a hydrocarbon that is mainly of carbons and hydrogens, the carbon-hydrogen bond itself is polar. However, the net result of all the carbon-hydrogen bonds within the molecule all cancel out, so therefore the molecule itself is nonpolar. As well, there are no lone electron pairs. Therefore, all carbon-hydrogen hydrocarbons are nonpolar compounds. And because they're nonpolar compounds, there is only one type of intermolecular force, and that's the London dispersion force. As you recall, these London dispersion forces are very weak. So therefore, their melting point and their boiling point are very low. Further, nonpolar compounds make them insoluble in water because water is a polar solvent, and nonpolar and polar liquids are not miscible. However, hydrocarbons are miscible in nonpolar substances. As we mentioned, because hydrocarbons only have London dispersion intermolecular forces, their boiling points and their melting points are very low. However, they do increase as the number of carbons increase. That is because as the number of electrons present in the molecule increase, there is more London dispersion force. Another factor that affects the melting point and the boiling point is whether or not the hydrocarbon is branched or is unsaturated, and we'll discuss this in the next slide. As we mentioned, as the number of carbons increase, the number of electrons present in the molecule increase, so therefore the London dispersion force increase, and so does the melting point and the boiling point. In general, 1 carbon to 4 carbon hydrocarbons are gases. This is methane, ethane, propane, and butane. Whereas 5 carbon to 16 carbon hydrocarbons are liquids, such as pentane, octane, hexane. And 16 carbon to 24 carbon hydrocarbons are solids, such as wax. Here is a table that nicely summarizes the trend in the melting point and the boiling point of hydrocarbons as the number of carbons increase. Here we can see definitive increase in the melting point and the boiling point as the number of carbon increases, therefore the number of electron increases, and therefore the amount of London dispersion force increases. Let's discuss the effect of branching on the melting point and the boiling point. Straight-chain hydrocarbons, they tend to have higher melting point and boiling point because they're able to pack closer together. For example, a molecule like this can pack relatively closely. Therefore, the induced positive and the induced negative charges on these molecules, which is the basis of the London dispersion force, are closer together. When the charges are closer together, the forces are greater. Therefore, again, straight-chain hydrocarbons have a greater dispersion force and therefore a higher melting point. Whereas branch hydrocarbons, something like this, with a branch, cannot pack closely together, and therefore the distance between the charges is higher, and therefore the London dispersion force is lower, so their melting point is lower. The degree of unsaturation of hydrocarbon, or actually the number of double bonds in a hydrocarbon, also serves to reduce the melting point and the boiling point. Once again, this is due to these molecules being unable to pack closely to one another. Here we have a drawing of a saturated hydrocarbon. They are able to pack closely together. However, in a molecule with a double bond, there is a kink or a bend in the molecule, and these molecules cannot pack closely to one another. As you recall, double bonds cannot rotate. Therefore, there is a bend or a kink in the molecule. The molecules cannot pack closely to each other, lowering the London dispersion force and lowering the melting point. Let's now talk about how hydrocarbons, in this particular oil sands, are refined. The demo we're going to do today is a fractional distillation of a mixture containing pentane and isopropanol. Isopropanol is a common term for a 3-carbon hydrocarbon with a OH bond or an OH atom attached to the middle carbon. We're going to predict first of all which of these will have a higher boiling point. Pentane, as you recall, is an alkane with 5 carbon atoms, and isopropanol, as we just mentioned, is a 3-carbon compound with a OH in the middle. The intermolecular forces present in pentane is just London dispersion. Because the molecule is not polar, there are no dipole-dipole or hydrogen bonds. However, in isopropanol, London dispersion force is present, as well as hydrogen bond, because there is a hydrogen attached to an O, and the carbon-oxygen bond is very polar. This makes the entire molecule polar, so therefore dipole-dipole bonds is also present. Because of the presence of the hydrogen bond and the dipole-dipole bond, we predict that the boiling point of isopropanol will be much higher. Here is an example of the fractional distillation. We have the mixture of isopropanol and pentane here in the bottom. It is heated. The mixture is heated, and in this fractionation column, the hotter compound, the isopropanol, will remain, whereas the cooler compound, the compound with the cooler melting point, the pentane, will go hop into the glass tube, reach the thermometer. The vapor will go into the condenser. The temperature of the condenser is very low because of the presence of the water. The water goes in from the bottom and out through the top. It cools the entire condenser, therefore it cools the pentane vapor, and the pentane will then be collected in this Erlenmeyer flask. Here in Alberta, most of our oil reserves are present in the Athabasca Oil Sands. These are sand with a mixture of bitumen and water in it, rather than a usual crude oil. Therefore, when it is extracted, it requires additional fractionation and extraction techniques to separate the oil from the sand. Oil sand, as the name implies, is mostly sand. There is 12% bitumen, which is similar to crude oil but only thicker, and 4% water. In order for the bitumen to be extracted and the water removed, it takes a lot of processing. The key to extracting oil from oil sands is to remove the bitumen from the water and the sand. The bitumen is actually a mixture of alkanes and cycloalkanes, as well as aromatic compounds. In order to extract the bitumen and the water from the sand, we need to exploit the different chemical properties of those compounds. Bitumen is nonpolar because it is a hydrocarbon, whereas water is very polar, and pentane is often added to these compounds because it is a nonpolar compound, and therefore it will dissolve the bitumen. The oil sand will just settle in the bottom, and the bitumen, which is now in the pentane, will float above the water because bitumen and pentane is less dense than water. At an industrial scale, bitumen is extracted from oil sands using hot water. Water is heated to around 80 degrees, and this melts the bitumen. Therefore, it will float above the water. And then, in the separation tank, the water is separated from the oil and the sand so that you have the 3 separate compounds. The bitumen is then further processed and then sold to international markets. Now, because this process uses a lot of water, there are environmental concerns and questions raised about the wisdom of using water to extract a fossil fuel. New research have been done, and these extraction methods use less water and can recycle the water used, but still it uses water, and environmentalists are still concerned about using water to extract fossil fuels.